Assalamualaikum and hi. My name is Nabilah and I will explain to you about question. The question stated that we have to design a process where we can recover 98% of toluene from 1000 kg per second of mixture. The mixture consists of 28% of benzene, 38% of toluene, and the remaining is xylene. To solve this question, we have constructed a diagram that consists of two distillation columns. For the first column, the input for the column is as given by the question. The temperature that we set for the first column is 95 degrees Celsius. For the top stream, we label the mass flow rate as M2, where 98% of only benzene is recovered there. For the bottom stream, we label it as M3, which consists of all the components. We label the unknown for benzene as A1, toluene as A2, and xylene as A3. M3 stream is also connected to the second column, or in other words, M3 is now the input for the second column. The temperature that has been set at the second column is 115 degrees Celsius. The top stream is labeled as M4, where the output is only benzene and toluene. The unknown for benzene is B1, meanwhile for toluene is B2. At M4, 98% of toluene from M3 is recovered here. We have labeled the mass flow rate at the bottom stream as M5, where the product is only xylene and toluene. The unknown for toluene is C1, and the unknown for xylene is C2. The pressure that we set for each column is 1 atm.
The concept that we use to perform mass balance is the conservation of mass. The law of the conservation of mass states that for any process unit, mass cannot be created or destroyed, but it can change from one phase to another phase or converted to another form throughout the process reaction. For example, let's say we have an oven, and then we put 1 kilogram of sugar and also 1 kilogram of flour. At the end of the process, we will get the total mass of 2 kilogram of the cake. Based on the example, we know that the total mass input to the oven, or what we call process unit, is 2 kg, and then we will get back 2 kg of the output. So the input and output mass are same. And then for the calculation of mass balance, we will use the continuous steady state processes. Continuous process means that the input and output flow continuously throughout the duration of the process, while the steady state process means that the process variables such as temperature, pressure, volume, and also flow rate are not changed with time.
Our first boundary is including feed stream with mass flow rate 1000 kg per second, overhead product stream M2, and bottom product stream M3, and the overall boundary equation is 1000 kg per second is equal to M2 plus M3. Based on the diagram, we can choose to calculate component balance for xylene and toluene as they appear less. For component balance xylene, we refer to the basic concept which is all in is equal to all out. Since all xylene appear to the bottom product stream, the equation will be 1000 kg per second multiplied with 0.5 kg xylene per kilogram is equal to mass fraction xylene, which is A3 multiplied with M3. Next, for component balance toluene also appear at the bottom product stream only, so the equation will be 1000 kg per second multiplied with 0.3 kg toluene per kilogram is equal to mass fraction toluene, which is A2 multiplied with M3.
And we have another two additional equations, which is it is stated that 98% of benzene is recovered from feed to the top product stream. So the equation is 0.98 multiplied with 0.2 kg benzene per kilogram multiplied with 1000 kg per second equal to M2 multiplied with 1.
And the other equation involving mass fraction for all substance in bottom product stream, which is 1 equal to A1 plus A2 plus A3. First, from the equation 4, we can calculate the value for M2, and the M2 value is 196 kg per second. Next, with the value we get from equation 4, we can calculate the value of M3 from equation 1. So M3 is equal to 1000 kg per second minus with 196 kg per second, and the value of M3 is equal to 604 kg per second. Next, with the value of M3 we get from previous calculation, we can use it to calculate the value of A3 from equation 2. And the value of A3 is equal to 0.622 kg xylene per kilogram. After that, by using the M3 value, we can solve for A2 by using equation 3. And the value of A2 is equal to 0.3731 kg toluene per kilogram. Finally, we can solve for A1, where we can use equation 5, and the value for A1 is equal to 5 multiplied with 10 to the power -3 kg benzene per kilogram.
So, from boundary 1, the value of m.3 has been calculated, which allows us to continue to the second boundary with m.3 at 804 kg per second, benzene, toluene, and xylene components with their respective values. So, the first equation is the overall boundary, which is 804 equals to m.4 plus m.5. Next is the component balances for xylene by multiplying its component part at the mass flow rate. 0.622 multiplied by 804 equals to C2 multiplied by m.5. Since it's only involved in m.5, which makes it equation 2. Then, for the component balance of benzene, which is 5 exponent negative 3 times 804 equals to B1 times m.4, makes up equation 3. Now, there are additional equations to consider, such as the final 98% toluene discharge. 0.98 times 804 times 0.373 equals to B2 times m.4, equation 4. And also B2 to be changed to 1 minus B1 since the total of both B components is 1, equation 5. Finally, 1 equals to C1 plus C2, equation 6. Now with all these values in hand, we can start solving by inserting equation 5 into equation 4, which will give us equation 7. 293.89416 equals to m.4 minus m.4 times B1. Then equation 3 into equation 7 since m.4 B1 has been calculated, which will give us m.4 value, 297.91416. From here, we can proceed to equation 1 and substitute m.4 to get m.5, which will give us 506.08584. Now that we have m.5, we can check in equation 2 since m.5 is involved to obtain C2, which is 0.9881. Now in equation 3, we can also solve for B1 since m.4 is calculated, which is 0.0135. Substituting value of B1 into equation 5, we have B2 value of 0.9865. Finally, in equation 6, we can calculate C1, which is 0.0119. That makes it up for every component in the second boundary.
Hi, my name is Sarah Farina, and today I will be presenting the justifications for our assumptions in our design process. Firstly, we must assume that both distillation columns are 98% efficiency. Distillation columns can never be 100% efficient equilibrium due to discrepancies as well as contamination in the columns itself, and therefore we could never actually achieve a 100% efficiency. Not only that, we have found boiling points of xylene, toluene, and benzene with boiling points of 139 degrees Celsius, 110.6 degrees Celsius, as well as 80.1 degrees Celsius respectively. These boiling points that we have found are crucial in our calculations because, as we can see in our first boundary, we intend to remove 98% of benzene since it has the lowest boiling point, and subsequently we remove toluene with the next highest boiling point, which is 110.6 degrees Celsius. And that is all. The references for our justifications, for our assumptions, can be seen in the next slide. And with that, I would like to summarize our video. Thank you.